Hi all. Today we will talk about the diode rectifiers, in particular single phase diode rectifiers. So they are also called line frequency diode rectifiers because the frequency mainly depends on what type of AC grid that you are connected to, and the general symbol is like that. So you have a grid here, and then the rectifier block is shown like that with a diode, but it can be like many diodes inside that block. And usually we have some filtering elements like a capacitor or a LC filter, and usually ID is shown as our output current. Okay, so there are again, similar to ideal switches that we talked last week, there are some properties that we require from an ideal rectifier. So as an ideal rectifier, if you are converting from AC to DC, I want to get a pure DC. So that means there is no ripples or anything, it's purely DC. But of course in practice it is not possible. So also I don't want to disturb my input current, so I don't want to cause any distortions on the input current, or in other words, I want to, if I have a perfect sinusoidal input, I want to draw a sinusoidal current as well, so that means that THD would be 0. So of course I want high efficiency, the power that I converted to DC would be similar to what I converted from the AC. So I want to make all that circuit as small as possible, so that means you will have high power density. So let's start with the simplest case. In the simplest case, let's talk a diode connected to a resistive load. So you can have a system like that where you have the source voltage, and that source voltage is connected to a diode, just a single diode, and then we have a resistive load. So let's talk about the output voltages. So it is quite simple. So of course, if you have a, let me try to draw it first, and let's say this is your input voltage. Let's say this is your Vs, so I have a sinusoidal input voltage. And what should be my Vd? So basically, whenever that voltage is larger than 0, let me use the red color for Vd. So whenever my voltage is larger than 0, so my diode will be on. Okay, diode is on. And whenever it is negative, whenever you have negative voltage and this is a resistive load, so the current would like to go in the opposite direction, but of course diode becomes off, and assuming it's an ideal diode, so the output voltage will be like that. So this will be my output voltage. And for current, again, since this is a purely resistive load, the current will be in phase with the voltage, and let's say this is your current. Okay, so this is what you can achieve. So this is basically not a full wave rectifier, but it is a half wave rectifier. It is only rectifying half of that circuit. So what about the average voltage? What can you say about the average voltage of the rectified waveform? So in other words, so what is the area under that thing, and if I take the average over one period, what should be the average voltage? So before that, let me ask you a simple question. So let's say you have a sinusoidal waveform like that, and let's say that area is pi, this is a sine, and I want to estimate the area of a half sinusoid like that, and if the magnitude is 1, what is that area? I want you to calculate it yourself. Actually the answer is really easy. so but you can make rough estimations, so I will just give you a couple of seconds to calculate that one. Okay, so either you can go, from the, if let's say this is sine omega t, so basically you want to get the integral of a sine wave from 0 to pi of a sine omega t, d omega t, whatever. So you can calculate that one. What is the integral of a sine? So basically it is minus cosine, from 0 to pi. So the value of that integral can be written as like minus 1 minus 1. So basically that's equal to 2. So that area under half sine wave is basically equals to 2. Right here. So 2. So that is, really important parameter that you should know. So if the peak of a sinusoidal is 1, the area under one part of that sinusoidal is equal to 2. Okay, our next question is, what is the average voltage in that waveform? So that waveform is basically following here, and then it is 0. So I can write the mean voltage, for that one is basically the average, that one, over 0 to 2p or 0 to ts. So basically v dt, okay, so that is equal to, all time length will be 1 over 2p, and that area is 2 here and 0 on the other side, so it is 2, so it is basically 1 over p. Of course this is for a waveform having a magnitude of 1, and here this is our peak value, and if this one is RMS, okay, so the peak value is square root 2 Vs RMS, and actually I can modify that signal with that one, instead of V1 I will use that peak value, so that will be square root 2 times Vs RMS divided by P. And if you remember from the last week, 2 square root 2 divided by P was 0.9, and this is half of it, so this is 0.45 Vs RMS. Okay, anyway, we will solve a few examples in the following slides. Cool. So now I would like to talk about what happens if we are not connecting a purely resistive load, but if we have an RL load. So in the RL load it will be something like that. So we have the same voltage source, the same diode, but instead of a resistive, we included some inductive load in series with the resistive system. So basically, let's go over about the voltage characteristics. I don't want to draw it all myself, but we can go through. So basically Vs, okay, let me use red one. So that one is my source voltage. So again, my source voltage is, sinusoidal voltage. Sinusoidal voltage here. So now, of course, in the previous one, remember it was a purely resistive load, but I have now an inductive load. So the voltage, that voltage will not be in phase with the current, and if you can think that inductor, so it will take some time to increase the current. So basically because of that, the current doesn't increase immediately and it's not in phase, but as you can see there is some kind of lag. So basically when the voltage reaches to maximum, the current didn't reach to maximum yet, and it actually delays a couple of later on, and we will talk about those things. Then after the current reducing, sorry, after the voltage reducing, the current actually start reducing after that time. And you can think that one as like a power factor, so that there's a lag between the voltage and current because it's an RL load, and basically current is lagging the voltage. So how does it change from the perspective of current or from the perspective of inductor? So from the perspective of inductor, so basically it is when the diode is in conduction mode. So here is Vs, and basically here you have the Vr, okay, and Vr is basically just a multiplication of the current. So basically inductor voltage is Vs minus Vr. So basically the inductor, if that voltage level is positive, so if Vs is larger than Vr, the inductor current will climb up, and if it is lower, it will start reducing. And actually we see it here. So this is Vr, and Vr is in phase with the current. So whenever Vs is larger than Vr, so there's a difference. So basically that difference is that voltage. So that, let me write here, so that is the waveform of inductor voltage. Okay, and actually you can write VL is equal L di over dt. So whenever the current, the derivative of the current gives you the voltage. Whenever the voltage is positive, the current increases. Whenever the VL is negative, the current decreases. And we can see it's here. So basically whenever Vs is equal Vr, so let me go to the previous slide, Vs is equal to Vr, so basically at that point VL will be 0 when they are equal to each other, and if they are equal to each other, VL voltage is 0, and if VL voltage is 0, then that means di over dt will be 0, so that means my inductor current reach its peak value at that point. Then after that, so basically you can see there is now that difference, okay, there is now that difference. So basically the inductor voltage goes below negative, and when it goes below negative, so di over dt is also negative, so the inductor current starts reducing. Okay, so there's the critical part. At T2, basically our Vs voltage reached to 0, but we still have non-zero inductor current. Okay, so it's because it is non-zero inductor current and non-zero VL voltage. From that diode's perspective, it doesn't really look into the Vs voltage, it just looks at the polarity at that side and that side. So if there is still some voltage difference, it will still conduct, and if there is some current passing through here, it will still keep flowing. And as a general rule, remember, you cannot turn off the inductor current immediately. It will take some time to turn off the inductor current. So because of that, let me clean these parts a little bit. Okay. So after that part at T2, Vs is 0, but inductor current is larger than 0. Okay, so that is our inductor current. So that means I will keep conducting until when? Until inductor current reaches to 0, because once it reaches to 0, then it would like to go back in that direction, but now we have the diode, then it will cut off at that instant. So the diode will get out of conduction when the current reaches to 0 and would like to flow in the opposite direction. So the question is, when do we have the inductor current 0? So if you remember the voltage seconds balance from the last week's lectures, so if this is a steady state, so steady state means it at I 0 is equal 0, and I at T3 is equal to 0. So it started at the same point and it ends at the same point. So basically I can write, that waveform, remember. So I can write I, at t3 is equal to 1 over L integral 0 to t3 VL dt plus I at 0. So in that way, I3, current at T3 minus I0 is equal to that, and if they are equal to each other, so that means that should be 0. So in other words, if I integrate the voltage area through that distance, it will be equal to 0. In other words, area A, okay, and area B, they should cancel each other. A is equal to B. Okay, so that is, it may sound strange at first, but you can derive it yourself, and it's a well expected behavior. So now let's look at, what is the effect at the output voltage. So now if I go back, output voltage is basically, VD, and that VD voltage is, equal to Vs whenever the diode is conduction. So my output voltage is not the resistive load, but this is my output voltage. So it is equal to Vs whenever the diode is on. So let me try to draw my VD. So it will come to here. So if it were a resistive load, I will have, only half of the waveform, but now due to inductive load, so I see a short amount of negative voltages at my output waveform. So now my voltage is, output voltage is that area, as you expect from a resistive single phase rectifier, but with L value. So I have a negative output voltage. Okay, so you need to be careful about that one. So of course, this is called, we will see more detailed examples in the following weeks, but it is really important that you understand that phenomenon for a single diode case, and we call that thing commutation. Okay, so diodes, continues to conduct for extended period because it cannot get out of conduction when the inductor current is non-zero, because VL is equal L dI over dt. If you just directly cut that one, that will goes to infinite, and the output inductor voltage will go to infinite. So we can't have that thing. Mathematically we can't have that thing, and that is why diode continues to conduct until the inductor current, let me write here, until the inductor current reaches to 0. Okay. So, and how does the average voltage change with the commutation? So before, just with the resistive load, remember I have that kind of waveform, resistive load. Let's say this is square root 2 VRMS, whatever VSRMS, and with the RL system, basically now I have that kind of VS. I still have the same peak, square root 2 VRMS, okay, but I have that area, okay, I have that area, and that part is the commutation period. Okay, and basically you can say again the average voltage is equal to 1 over T, V Vt dt, and basically because of that commutation period, it will cancel some of that area. So as a result, your output voltage, average output voltage is reduced. Okay, so we will see more detailed calculations, but for now you can say commutation basically reduce our output voltage.